So let's begin the last talk. The speaker and the organizer is Mee Seong Im from Johns Hopkins University. I'm a little bit confused because the title in the sheets and the title here is different. So I think she's talking about entropy, cocycles, and diagrammatics.
Thank you, Hyungkyu, for organizing this conference with me. And I had fun organizing with you. And I would like to thank Hyungkyu to invite us, Mikhail, myself, to be part of the organization, because we met over the summer and we decided to organize a conference. So we spoke for a long time and there were many emails going back and forth. So that's how, this conference came together. So it's good to be back. It's been 20 years since I came back, but then I was here a little bit over the summer. So it was good to explore and learn a lot. And I'm still learning a lot during this visit. So actually, I have 2 talks planned. You could see there's 2 sets of slides, but I'm not going to be able to go through everything. So I'm just going to stick to this. The other one is about parabolic induction of nilpotent orbits. You have a nilpotent orbit, and then we induce it up to a nilpotent orbit over a bigger Lie algebra. But how do you do that over type A, type B, C, D? This is for Springer fibers. That was the other talk. This is more diagrammatic and categorical sense and entropy. So I thought maybe I'll do this one. Maybe it might be better fit for this audience. If you have questions about the other talk, feel free to talk to me afterwards. So this is joined with Mikhail Khovanov. So for, let's say G is uppercase G is a group. That's the point. Okay, so uppercase G is a group. And what we want to do is you want to consider lines on the XY plane with the co-orientation. So, as you have seen all day or the last many days, orientation means arrows are pointing upwards, right? Or downwards. But co-orientation is like a normal direction, co-normal direction. So they're going to point in the left or right in the direction of the lines. The lines are labeled by elements of the group. So here's sigma and tau. The lines are going to merge. So in this case, the lines are merging, or when they go up, they're splitting. So mathematicians, we read the lines from bottom to top, and then concatenations of such diagrams, we are reading from right to left. So this is a mathematician notation. Physicists, they're doing the opposite way. You read from top to bottom and then left to right. Okay, so in this case, so in this picture, we have a monodromy and then we have a vertex. So we could draw this thicker to make it more clear. But here at each vertex, you have what's known as monodromy. So monodromy means what you're doing is you're going around that point and you're reading the labels, all the edges connected to that vertex. You're reading all the labels and just multiplying them. Let's just say the group action is multiplicative. So if you're moving in the direction of the co-orientation, you just multiply, you just write down tau. But if you're moving against the co-orientation, you write down the inverse. So in this example on the right, let's just go around clockwise. So what we're doing is we're writing tau times sigma tau inverse. And as you can see, when you write this out, this is just identity. So we call this is a trivial monodromy. What we can do now, you can introduce a dot on the line. A dot is codimension 1. On the line is codimension 1. This is called the defect. It's a sub-manifold. So we're just working with lines here. So if you have a co-orientation pointing to the left, let's call that sigma. But when it passes through the dot, you change the co-orientation. Just change the orientation, co-orientation to be the other direction. So that's sigma inverse. So as you do, what you're doing is you're adding more and more decorations, and what you're doing is you're forming a network. Network just means graph. In this case, this is a closed network because the lines they can go sort of towards infinity, but in this case, they're all closed up. Here, so as you can see from the previous picture, you saw a point P on the network. Point P, and what we can do is we can define what's known as winding number. W omega of P comma N. Script N is going to be the network. And as you can see from here, what we're going to do is you take the point P and then you push it out to infinity in any direction. And what you're going to do is you're going to read the labels of intersection points. So let's come back to this picture. So you have a point, and let's just say you're pushing it out to infinity. First, you're crossing tau, then you cross sigma. But if you push it out to infinity this way, you have gamma inverse. So you have gamma inverse. What's next? And then sigma tau gamma. Multiply that by sigma tau gamma. And what you end up, when you simplify, you get sigma tau. So it's invariant. It doesn't matter how you push it out. What you can do is you pick a point and you just push it in any direction, you get this invariance. Yes, it's on the region. Yeah, it's on the two-dimensional, the simplex. Yeah, exactly. So yeah, you pick any point and you're starting to create some invariance. So this is what I just explained. No matter how you push it out, you're gonna get sigma tau or sigma tau, element of a group. So we're gonna eventually create this monoidal category. But right now we need equivalence relation. Okay, so equivalence relation, we're working with co-normal directions, but there's a duality here. The arrow edges can point to the left or to the right, or point up like this, point in the direction of the lines. So what we can do is later on, you can work with this co-orientation or orientation. So there's this duality, but then, okay, local relations. So here, this is associativity. What you can do is you have three lines merging at the same time, so you can just pull them apart however way you want. That's what this thing basically means. You can have first two lines merge, and then it merges with the third line, or you can have the number 2 and number 3 merge, and then that string merges with the first line. So it's basically saying no matter how you merge, you have this local move. And then whenever the lines merge, here's a sigma line on the left, tau on the right. When they merge, the merged line is just going to be sigma tau. And then let's just make the notation, just read from left to right. And then when the sigma tau portion merges with the gamma line, then you just multiply all the group elements together, you get sigma tau gamma. Whenever you have an empty you have a circle with nothing inside, with the orientation pointing outwards, that's just going to be empty. Just erase all of those. And then here's another one. Here's like a surgery. Whenever you have arrows pointing in, you can cut it, and you're connecting the top two vertices, bottom two vertices, and things are pointing up and down, inward. It's the same thing. If they're pointing outward, you do the exact same, similar kind of surgery. Okay. Now, what we're going to do is, remember, you saw the closed network. You can cut it, slice it however way you want. And we call this network with boundary, so outer boundary. So those are the dotted line. You slice it. So in this case, we can build a category that's monoidal. So what we're going to do is, when you read along the bottom, these are the elements of group. These are the group elements. Sigma tau, gamma is pointing. We have to pick a notation. So whenever things are pointing to the left, we call it sigma tau. But whenever things are pointing to the right, put an inverse. And so the elements of the object, these are the objects in a category. So whenever you see a whole bunch of group elements along the outer boundary from bottom to top, what we're going to do is just do a tensor product of the objects. So in this case, yes, it's a function. Yeah. So the strings are actually cobordisms. Yes, it's a functor between it's a morphism. Yeah, morphism. So you have x sigma plus. You tensor that with x tau plus, tensor that with x gamma plus, and tensor that with x gamma minus. And then this guy will map to s and then x sigma tau, and then with the plus sign, because things are pointing to the left. And then what you can do now is you can stack a lot of these pictures together, concatenate them. Whenever things don't match up, they evaluate to 0. And you can also see that this category, together with because of the relations, you get a pivotal category. You can bend these diagrams. So pivotal basically means whenever you have these objects, you also have a dual object in the category. Okay, so this is just a side remark. So whenever we have a closed network, it's cobordant to an empty set because the classifying space, the BG is equal to 1. We explain this briefly, but we don't talk about it extensively in our paper. Because what we're going to do is you look at the planar G network without dots, and then you can sort of think of, you're looking at the Poincare dual of a network. So it's basically thinking of the sphere into BG, and this is contractible because the higher homotopy groups are all trivial. And then pi 1 of BG is equal to G. Another way of thinking about this is the associated universal principal bundle has a contractible total space. We see there's a very little freedom in the category because when you have a product of corresponding objects to another set of objects, there's going to be a unique morphism going between one object to the other. So they're uniquely determined. Like what we saw before, this picture is, we're going to see that this is useful in physics when we have defect, because these are the defect lines that merge and split.
The second line can be interpreted as a map from what? As a map.
You mean up there? It's a map?
Second line.
Second line as a map?
From what?
As a map to the classifying space.
From what?
Map to the space. Oh, it's a planar G, it's a G network.
You mean what map is from something to something, right?
Yes.
What from?
It should be, what we're thinking is you can think of it as S2 into BG. Yeah, S2 into BG, this part here. Now what you can do is continue to think. Now you have representations of a group G. You put points on the surfaces, like on the plane, not the plane, but then like on the region. So let's label X is an element of U, and U is going to be a representation of G. So the left picture here, dots are labeled by elements of U, which float in the region, and then they move across the lines with co-orientation. When you push it, let's just say you push X past this line, you have sigma acting on X, but you don't know what it is yet right now. Whenever you have a whole bunch of dots, we have this additive property. Just put one dot and just add all the elements of U together. Just label it like this. Okay, to explain the previous picture better, how do you go from the first to the last? What you're doing is you're pushing the point X, and then eventually this bubble pops out. Or actually you can use a local move, right? Could use a scissor and you locally cut around this, like this cup and a cap, cut it, and then that becomes, the left and the right parentheses. So you get a circle, and inside it you have this point X. So the point X is absorbing the circle with the co-orientation. So that's how, and then you label the dot with sigma of X, and then this line, just leave it alone with co-orientation. Okay. You also have a torsor. A torsor is a copy of the representation U, but without a distinguished element, which means U is acting freely and transitively. So if the top and bottom sequences, when you multiply upon multiplication of the labels, and then what you do is if they match, the hum space is just going to be a copy of U. So that's how you can view this as U torsor. If the top and bottom sequences, they do not match, then there is no hum. So you're just going to be empty. The cobordism will just be empty. Now what you can do is, so if you notice, we're creating this new diagrammatics in the context of, so you're starting with basically nothing, and we're building more and more, building this up. Now you throw in this blue wall on the bottom. So let's say you have group elements sigma and tau, and they merge. But what you can do is this blue wall on the bottom, you can think of it in terms of there's a vertex, they merge, so you have a vertex in the middle. It's gonna do this absorbing, it's like sucking it in. The lines, it sucks it in, and then what it does, when it sucks it in, it pops out the C of sigma tau. And remember, let's read everything in order. Sigma's on the left, tau's on the right. So write it like the C of sigma tau. I'm gonna explain later what is C. Now when you have a split, it's gonna absorb the black dot, the black vertex, it's gonna suck it in. So you have two lines that's pointing to the left, and it pops out this same thing. It pops out a dot on the left, and but with the minus sign, minus C of sigma comma tau. These dots, we're gonna call, okay, the two dots, yeah. Where's U? U is gonna be a representation of G. Yes, representation of G, good question. Yeah, so this is some element of U. So these black dots here, the vertices, these are additive vertices. Yes.
Blue,
The wall, yeah.
that's the boundary.
Yeah, it's on the boundary, yes. So what you can do is you can introduce new concept called this black wall. And then it probably I think it appears in physics, like there's a lot of particles being absorbed or being released or being emitted. That's what the blue wall represents, eventually. Yeah, eventually, yeah.
In the picture, you try to get dot, you see over sigma tau. Where's the origin? Where is the origin coming from?
Where is it coming from? Oh, you're gonna see in a little bit. You'll see like, what is this? What do they see? Yeah. We have to call it something. It's a combination that's sort of connecting sigma and tau that are related to each other by something. So C is some like a function.
We have two ways.
Yeah.
This kind of thing. Without dot, with dot.
Yeah, exactly. Without the dot, the category is really simple, but now you can make it much more interesting. So you're having this categories sort of sitting inside. Yeah, making it bigger and bigger and more interesting.
How about the invertible, non-invertible?
Huh? Invertible?
Invertible or non-invertible?
Yeah. Yeah, so you can sort of think of it as sort of dual, right? You can think of it as you have this picture and then you push it together. So this is sort of sucking in the black dot. It disappears, right? So it's reversible direction. Yeah. Yeah. What is, it just means like because it's sitting on the region, not on the line. It's not sitting on, yeah. Yeah. What does it mean by element of U? Oh, you're gonna, because this dot is sitting on the surface here. It's not sitting on the network. Oh, it's a representation of G, anything. It's much more vague and abstract. Later on, we're gonna work, right now we're working over field K. We could work over finite field too, but later on, when we be more specific, make K to be real numbers, then you'll see more connections. Okay, so now what is this condition on C? Remember, we have these local moves on the upper left corner. So, we have this local moves, but then according to the blue line, it's gonna absorb that vertex, the leftmost vertex. So it's gonna suck it. Those two edges are gonna be sucked in. It's gonna pop out. It's gonna be sucked in and it's gonna pop out. C of sigma comma tau. You have another like these merge coming in, right? Merge picture. So that other vertex here is gonna suck in that vertex and another dot's gonna pop out, labeled sigma tau and then comma gamma. And then remember additivity, you just erase that. I don't have space. I didn't have space. So what you can do is put one black dot on the left of this on the left of this line with co-orientation, and then just add the C of sigma tau and then plus C of sigma tau comma gamma. Just add them together. And then you also have this local moves, this local associativity relation. The first two edges merging in together, that's the same thing as the second and the last merging in together. So you have the associativity relation and you play the same game. It's gonna suck in these two lines and it's gonna pop out this black dot labeled tau gamma, C of tau gamma. And then you push it to the left and it's gonna have the sigma action on the C of tau gamma. It's gonna absorb the circle labeled by the group element sigma. So you have this guy, and then you play the same game here. It's gonna absorb this guy, and then you have C of sigma comma tau gamma, and then you add them all together. These two, replace it with one dot labeled with the sum. You see the sum of those two is equal to the sum of these two. So there's some relations that are naturally coming out, and you're gonna see that. The relation is precisely this. This is called the two cocycle, the multiplicative version. There's a C of sigma tau plus C. You move the first two letters to the first coordinate, sigma tau comma, throw in a new variable gamma. That's equal to C of last two letter tau gamma, but there's some kind of twisting action. Sigma action, it doesn't have to be trivial group action, plus C of move tau and gamma to the second coordinate, and then you throw in the first letter, sigma. This is called the two cocycle, and which appears in physics papers and like Witten. It appears in a lot of papers in mathematical physics. But then using the pictures, the diagrammatic, that would be another way to think about the two cocycles diagrammatically. And it appears naturally. Yes. Yes. Sigma is a two cocycle. Sigma is actually element of the group. Yeah, so yes, should be C. Thank you. So what we're basically doing is you start out with the original category and you make it bigger and bigger and you modify by adding in more and more defects, make it much more interesting to the point maybe it represents or it could model, it models something in physics or some other interesting categories. Okay, I'm gonna go in a different direction. So now let's talk about Shannon's entropy. We heard about entropy earlier this week. So I'm gonna talk about Shannon's entropy for finite random variable. Let x equal to x1 through xn, that's gonna be a finite set. Shannon's entropy of a probability distribution, p sub x, on the finite set, what we're gonna do is over each point, x1 up to xn, you're gonna assign finite probability, p1 up to pn, so when you add them up, it's equal to 1. The pi's are bigger than 0, less than 1. And then Shannon's entropy is defined to be negative, the sum of the pi log of pi. Many people might be familiar with this. Let's say n is equal to 2. Then let's simplify, get rid of the subscript, erase all that, make p equal to p1. Then you just have two terms. So, and then remember, p1 plus p2 is equal to 1. So p2 is equal to 1 minus p. So what you can do is write it like this. So the entropy now, you can write it as, and the random variable for this guy, p comma 1 minus p, that's minus p log of p minus 1 minus p log of 1 minus p. So it's very nice. P is a real number between 0 to 1. Okay, but now what you can do is extend it over all real numbers by defining this, extending it like this. When p is equal to, when p is between 0 to 1, you have this over the Shannon entropy. And when p is equal to 0 or 1, you just make it, when you plug in 0 or 1, just make it equal to 0. And then over all the other numbers, what we're going to do is just log of, just put an absolute value sign. So you extend it to over all real numbers. So it looks like this. It's a continuous function now and unique. Psi over from real numbers to real numbers. Psi of a, let's define that to be minus a log of a, absolute value of a. This is the derivation. So if you're going to expand this, you can check psi of ab, that's equal to psi of a times b plus a, pull out the a times psi of b. Well, it's not linear. When we can check, right? Log of a plus b, absolute value of a plus b. That's okay. So now, okay, we have the more general form. If a is equal to these probabilities, a1 up to an, then this Shannon's entropy, you can write it as the sum of the psi I, these are derivations, minus the psi of the sum. And then now when all these guys add to 1, what is log of 1? That's 0. So it disappears. And what you do is you get the Shannon's entropy back. Okay, the Shannon's entropy H. These are also famous equations. They satisfy these relations. P and Q could be anything. Let's say P is not equal to 0 or 1. Then you have this four-term relation. Four-term meaning in terms of the H. H of P minus H of Q plus P times this guy plus 1 minus P times this other guy. Q, H of 1 minus Q over 1 minus P is equal to 0. You can rewrite this, just manipulation to make it more symmetric. You get this guy. H of P plus, and this side you have H of Q, and the other on the left side you have 1 minus P, 1 minus Q on the right, Q over 1 minus P, P over 1 minus Q. So we can work with the second relation. Huh? What's the function of H? Oh, that's the Shannon's entropy, minus sum of Pi log of Pi. Yes. Yeah, A, uppercase H always means Shannon's entropy. Yes, yeah. Okay, now we have Capiliano. So in his paper, let's say K is going to be a vector space. K is going to be a field of characteristic 0. What he does is he creates this vector space here, J of K. What are the spanning elements? They're spanned by two symbols, A comma B. A and B are elements of K, and then the vector space satisfies these three relations. If you have the symmetry, A and B is equal to BA, you have the scalar multiplication, CA comma CB, and what you can do is you pull out the C, it satisfies this, and then you have this 2 cocycle again. This is the additive version. So you have BC, B comma C plus, and then you move B and C to one side, throw in the letter A. That's equal to A comma B plus, and then you move AB to the left, and then throw in the new letter C. We can use, using the three relations, is usually use this relation. And you could see that A comma 0, 0 comma A, these are going to be equal to 0. And you can, what we do is you can prove these using these relations. Okay. So J of K is known to be infinitesimal dilogarithms, and these are infinite dimensional. Yes? Question?
It's not A, B means.
Yeah, it's a vector space with the unusual symbol. It's just a vector space, elements, yeah. So that's a spanning set, yeah. You're gonna see another vector space soon, so it has a different symbol, and together with relations, yeah. Okay, so it was observed by Catalano and Kontsevich, and then it was also independently by, see the review by Tom Leinster, that you can interpret this entropy in terms of this 2 cocycle for affine group of symmetries on a line, affine group of symmetries of a line. So what you can do is you have this Catalano's vector space, symbol A comma B. Let's just define it to be this, A plus B times the Shannon's entropy of A over A plus B. And if the denominator is equal to 0, set it equal to 0. What you can do is you can extend this entropy for 2 variables with this formula. Let me see. So this A comma B together with the subscript H is basically too much details, but they satisfy Catalano's relations. If you want to write in terms of the right-hand side, they satisfy Catalano's relations. This is for the affine symmetries. Okay, you can rescale by C. So this is the affine group of a real line, C comma CA01. C is a unit, A is a real number. And then you have this group of affine symmetries where X is mapped to CX plus A. C, okay. And these are real numbers. What you can do is we can view this 2 by 2 matrices as a pair. C comma A, C is a unit, A is going to be a real number. Or you can twist it the other way. We can extend this bracket notation to a 2 cocycle on the affine, the group of affine symmetries, where you have this guy, A1, C1, together with A2, C2, and that's just equal to A1, comma, and then C1, A2 in the second coordinate. You're going to see why in a little bit. Okay, now we have this thing called graphical calculus of entropy. Okay, remember, so now, keep in mind the block lines when you merge. Okay, we're working over, okay, so here A and B, and then when you merge, let's write down the merged line as A plus B. Over the vertex, when they merge, over that one vertex, you label that guy with A comma B with a bracket notation. And then when things are splitting, did I write that down here on the, okay, so when things are splitting at the vertex, you write down A comma B, but with a minus sign. So same kind of story. And then when black lines are crossing, these are called virtual crossing. It doesn't matter. It doesn't give you anything. So there is no intersection there. Red lines are now considered multiplicative lines. So, you're sort of still enhancing the category in some sense, right? So what we care about is you have this red line pointing in the left direction. And remember, you're reading from bottom to top, so all the points here are labeled by A, but when you cross this red line, every single point is labeled by C times A, so you rescale. When the red lines, when they merge, we just multiply them, like this. And you can also introduce this red dot where you have all the points on the left, on the bottom, you write down C, But then when you pass the red dot, you write down C inverse. And these guys are given by co-normal or co-normal orientation, right? Co-orientation. Okay, and then we also have, okay, let's check. So the vertex on the, okay, so here, the vertex where they merge, at the vertex, additive vertex, we have, is labeled by A comma B. And then all the points after that, they're labeled by A plus B. But since they merge, that point right there, the additive vertex, that will be labeled by A plus B comma C. And that's equal to, okay, and then these two guys are merging on the right. Remember, these are local relations. The vertex there will be labeled by B comma C. And then all those points in the middle will be labeled by B plus C. And then when these guys merge, that will be A comma B plus C. That's two cocycle relation. Everything is really simple, but all the mathematics that we've studied already exist. And then all we need to do is put the diagrammatics, create diagrams, just play with it, and everything is very consistent, and they all appear naturally. For this guy here, remember that vertex is just a virtual crossing. They're just passing through each other. So what this is saying is that over that vertex on the top, when over at the point merge, when they're merging, that point is given by B comma A. But that point here, the additive vertex is given by A comma B. So it basically means you have a symmetry, right? That's another relation of Catriano's vector space. BA is equal to A comma B. So all the relations are, they're all Catriano's relations, everything appears naturally.
How about the orientation? You have the orientation or the same, what kind of same orientation?
Yeah, we could do, you mean co-orientation? Yes, we can work with co-orientations, or we can work with orientations now because the multiplicative lines have co-orientation. The red lines they point to the left or the right. So in order to make the diagrams more simple, we use orientation.
Look at this kind of the A, B, C, and the A plus B.
Yeah.
Look at hidden symmetry.
You mean here?
No, okay.
Yeah.
And then some hidden symmetry.
Mm-hmm.
For example, we have the two A's without any kind of hidden symmetry, with the hidden symmetry.
Yeah.
And then how to get the distribution?
How do you get?
How to distribution? Without any kind of hidden symmetry. With hidden symmetry, how do you distinguish among these situations?
Oh, how do you distinguish them? It basically means you can work with this equation on the left or to the right. Whenever you have, but then they coincide diagrammatically. All the local operations that we have been doing as people in knot theory and low-dimensional topology, everything already appears. Like they match up with a lot of the constructions from the 70s and 80s. Yeah.
Look at like this. So you have the set up this kind of thing, and another you have line defect, and then
yeah.
Move up this line up to left, and then what happened? That is my question.
What happens to what I'm looking at is like the sum of the additive vertices. But then you can also throw in the blue lines, right? And you have the similar kind of pictures appearing, similar kind of story in terms of if you add in the blue lines, yes. Yeah. But then I'm also throwing in the red lines now, introducing the red lines that has multiplicative structure. Yeah, maybe I could talk to you after. Okay, now throwing the red lines. So notice that I said push all the additive vertices, push it out to infinity. So sort of imagine you're pushing all the points out to infinity and you want to observe like what's happening. So the pictures are actually much more complicated, right? So you see all the black vertices and you push them all out to infinity to understand the structure or like the local, the state space, the state space or the system. So here, the points here, A is going to pass through the red line. So all those points are labeled by C. They're rescaled by CA. All those points up there are rescaled by C. So those points represent CB. So what this represents is that when you push the point out to infinity, you have CA comma CB. But then this other picture here You just push it out to infinity, but the red line doesn't have to be like this. Remember, these pictures are up to cobordism. You can deform it and move it, or you can twist it, the red lines. You could twist the black lines however you want. It could be a tangled mess. I just made them very simple. Eventually, when you push it, there might be some cancellations, but you push it out to infinity. What you're doing is you're just doing C times this A comma B. And you have this other relation, and that's a scalar multiplication by Cartesiano. That's another relation. Yeah. And when you have black lines and red lines, they do not intersect, meaning you can pull things apart, just try to simplify the mess. So that's what this here means. So those vertices, there are no vertices. There's nothing there at the intersection. Okay, what about when arrows are pointing downward? When things are pointing down, so here, what you want to do is look at the additive vertex, and then as you can see from this picture, you rotate it counterclockwise or clockwise. So let's rotate it counterclockwise. So locally, when you zoom in, you can just zoom in here. See, this is really a merge, and we're already familiar with this. We do not have to throw in more rules or relations here. So you have a merge. So we know how to analyze this guy here locally. When you twist it, clockwise, here locally, this is also a merge. And it's the same thing. Now, when you have this guy pointing down and then they're sort of split, what you do is rather than coming up with a new relation, you rotate this clockwise or counterclockwise. So you rotate this counterclockwise to see, we already have relations here. It's a split, and this guy here is also a split, because remember, you're reading from bottom to top. So that vertex really represents this guy, A comma A on the left. It should be A on the left. It doesn't matter now, right? Because of symmetry, A comma B or B comma A, it's the same thing. But because it's a split, you have a minus sign. Whenever you have a merge, like this guy, you have a plus sign, positive sign. Okay, now what we do is, as we continue, we have this isotopy, which means the diagrams can bend and you can stretch and pull things apart. And then when you analyze all the additive vertices, add them all together, you're going to get the same thing. So here, the vertex on the left, A2 is going to pass through C1. So you have C1, A2. And then when these guys merge, the additive vertex represents A1, comma, C1, A2. And then when these, that would be this point. The vertex represents this guy, but the black lines are merging, so you just add the elements together. A1 plus C1, A2. And then here, the red lines are just multiplicative. So what you can also do is, there's a lot of things going on. You can also look at the boundary points, A1, C1, and then A2, C2, and then you have this, there's a multiplication rule which coincide with the group of affine symmetries. You have A1 plus C1, A2, comma, C1, C2. So that's A1 plus, you multiply these guys together, C1, A2, and then the last two coordinates will be C1, C2. If you do the matrix multiplication, right, CA01, but change it to C1, A1, 0, 1, C2, A2, 0, 1. These are exactly what you're going to get. These are the coordinates of the group of affine symmetries. So here, what we can do is we can extend from the real numbers. We can extend this to a 2 cocycle on the group of affine symmetries by defining A1, C1, A2, C2 by A1 and then comma C1, A2. The 2 cocycle on the group of affine symmetries, this is not a co-boundary. The restriction of this guy to the real number is a co-boundary because of this derivation from earlier. So that was just a side note. Now, so here we have another K vector space. Let's call it beta of K. This is also given by Capriano. It was in his paper. It has a spanning set given by brackets A. This is also infinite dimensional. A is a unit. And then and then together with the relations, the bracket 1 is equal to 0. And then you also have this 4-term relation, 1, 2, 3, 4, and that's equal to 0. A is not equal to 0 or 1. That guy up there is similar to what you saw here in terms of entropy. Yes, it's just change A and B to P's and Q. Yeah, yes,
The thing of spanning set, What is the spanning set?
The generators, the spanning set, like all the elements. Okay, we're constructing a new vector space. What are the elements in the vector space? Yes, yes. Yeah, generators together with the relations. Yeah. It's actually the fourth term here, 1, 2, 3, 4. So you have 1, 2, 3, 4, or 1, 2, 3, 4. It's actually it's a deformation of 5-term limit, actually. And then I prove it in my paper with Mikhail, as well as it's also given. Some information is given in other papers, Sager. What's you mean A minus B? We have to simplify like exactly what is the vector space, like how do you understand this vector space? So notice that before you had vector space given by 2 letters, right? A comma B. Now you have a vector space given, that's spanning set is just given by 1 letter A. So, are they ordered? Yeah, we could simplify, make A equal to B. No, maybe things simplify, but it's a construction of a new vector space with the special relation, and that'll play an important role later. Yeah, so it's basically saying you can think about J of K, Catenarius vector space, in terms of beta of K. And we'll see like how are they related. Yes, It works for finite field too, yes. Yes, good question. Yeah, so this is actually coming from 5-term relation, 5-term equation for dilogarithm, but when you do this deformation or take a limit, it becomes 4-term. That's why we call this infinitesimal dilogarithm, not just dilogarithm. Yes.
Vector space generated by that.
Yes, vector space generated by the spanning set. Yeah. Okay, so we can also view entropy as a function from this new vector space beta of R into real numbers R. Remember when we're talking about entropy, we're studying probabilities or probabilities. So we have to work over real numbers rather than more abstract field K. Only condition is that H has to be continuous. And H is actually a unique continuous function which respect or the 4-term relation as we saw before.
So here it's what is the relation between 4-term and 5-term?
The 5-term? Oh, that's kind of long proof. I can show you. I have separate set of slides that give you the proof, or 2 different proofs. Yes. So, okay, Catenarius proves that his vector space J of K is isomorphic. You can think about it as beta of K. They're the same thing, basically. And then the map is given by maps to A comma 1 minus A. And the inverse map is given by A comma minus A goes to 0. All these guys will go to 0 backwards. And then, from J of K to beta of K. And then A comma B will go to this guy, which is, it should remind us of entropy. Okay, and then Catenarius also proves that the second homology of the group of affine symmetries over the field K, K sub R just means right multiplication. It's isomorphic to beta of K and J of K. Here, the group of affine symmetries, Cx plus D, is going to act on K just by C inverse, because it's right action, just right multiplication or right translation. It's kind of, maybe I'll come back to this because I still have a lot to go through. Page 31. Okay, so now you have this cobordism again, but then so I think a lot of us are understanding these cobordisms better. But so whenever you have a map from set of vertices to a set of vertices, you have this cobordism, you have these maps. The black lines are additive, the red lines are multiplicative. And then what you do is, so what is this J of gamma? Gamma represents cobordism. And remember, even though I drew this, you can move the red vertex there, push it, like it could be in that quadrant, push it up, or it could be in that quadrant, like it could be anywhere. Remember, so this is just very simple. So there's many, many ways to deform this and twist it and move it around. What we're gonna do is J of gamma is, what you have to do is look at all the block vertices, add them up. Find what they represent and add them up. So here, you have a split. So one of the edges is gonna be A1, the other one's gonna be A2. It doesn't matter. You remember by symmetry, it doesn't matter. And then because it's a split, you have a minus sign. That block vertex up there, remember A2 is gonna go through C1, but with an opposite co-orientation. So you have C1 inverse. And the C1 inverse A2 merges with A3. So that block vertex represents this guy here. C1 inverse A2, comma A3. But you do that. And then this vertex up there, if the bottom edge represents this complicated chi, it doesn't matter. When you do a split, you just cut this thing in however way you want. One of the pieces, it's fine to just use one of the pieces will be labeled by this. The other piece will be labeled by A4. And then, so that element right there, that's given by C2 inverse A3 and then comma A4. The three block vertices, additive vertices, just push them all to one direction or push them all to the left or to the right. It doesn't matter. Just push them all, or like in the imaginary sense. When you do that, how many red lines is it going to go through? The multiplicative line. Nothing here, so you multiply by 1. That block vertex is going to pass through C1, and then in the direction of the co-orientation, so you multiply by C1. This last vertex is going to pass through C2, so you have to multiply by C2, and it's going to pass through C1, so multiply by that. If it's going to go through the 2 red lines and come back and then go back again, you multiply by C1, C2, right? Everything cancels out. And when you simplify, if you simplify, you get this. But this guy here, this is actually, the coefficients are called the winding numbers. And this is actually an invariant. No matter what cobordism you have, you twist it and make it really messy, you're always gonna get this guy. So it's unique to the cobordism. So you have block lines that are merging. All you need to do is keep track of the block lines. So we came up with this invariant for the cobordism. Okay.
About the horizontal, we have the vertical, the horizontal side, we have only the vertical. Horizontal is the same thing, should be there.
You mean like the outer boundary? The outer boundary is horizontal? Yeah, you can sort of think of it as like it's inside a box, dotted box. It could be much more complicated system, and you analyze locally or use local moves or start simplifying using the local moves. And there's not a lot of local moves, keep in mind. You just pull things apart. It's really, really simple. But the thing is, there's really deep structure that exists that no one knew until we thought about it. That's the thing, that's the point.
Locality and the diffeomorphism.
Locality
and the diffeomorphism.
Locally diffeomorphism? Yeah, I mean diffeomorphisms work because we're looking at strings. So you're looking at you're looking at isotopies. So right now there's not a lot there. We don't have rigid structure. Okay. We could look at geometries associated to these later.
In the one more.
Yeah. Yes.
I don't think there's a worry.
What are you worried about?
Higher
morphisms.
Yeah.
You mean like the other? What we do is we concatenate these. We stack all these pictures on top, and then everything will still come together. Like when you stack pictures on top, more of these cobordisms together, and then you will still. The letters have to be compatible. If they're not, they're gonna evaluate to 0. Nothing. Exactly the same. But the cobordism will each time you will get an invariant. Yes. And then the coefficients are the winding numbers, and these are all related to like entropy and Castigliano's vector space and the other vector space. Yes. This is the more general way. The P really means you're summing over all the additive vertices of the cobordism gamma. And then this omega of P gamma, that's just the omega, the winding number, what you saw earlier. S of P means sign of the additive vertex P. We just sum over that, and then we get this element in Castigliano's vector space, J of K. And this paragraph just explains how do we do this? The previous page, how do you actually come up with the invariance? Okay, now let's restrict to real numbers. So let's just say all these points, P1 up to Pn, and then they sum to 1. The P1 up to Pn, they sum to 1, and then they basically represent this guy here. P1, maybe I should look at this. So what we can do is you can label by probabilities, and then when they all add up to 1, and then just crunch them all together, it doesn't matter how they merge. What you do is you get this entropy for P1, P2, P3, or many, many probabilities for this entropy. Huh? Here, what is uppercase R? R inverse. I don't think I added that on the slide. Oh, actually, I think it's. Let me go back. It's this R. This R, yeah, this R. The isomorphism, which is given by this. Yeah, so R inverse will be given by this map here. That's right. Okay. Okay, and then you look at, so now the point is you come up with the diagrammatics that connects to physics and probability theory and many important papers like Cataldiano's papers. And now this relation works for chain rule in terms of probability theory. What you do is like the P1 up to these guys, they add to 1. But then all those points there will have to pass through P1 edge. So all those points are labeled by P1. All these points has to pass through Pn, so you multiply by Pn. And then these guys, when you add them all up, is equal to 1. So it's basically, this is a rule in terms of entropy or probability theory. What you can also do is like you deform it, but you can also push the red lines down, which means this is a relative, right? What is this? Conditional probability? Conditional. So P11, when you pass it through the P1 line, you have P1 times P11. All these points represent that. P1 times PK11. When you add them up, you just get the P11 up to PK1, 1. That's equal to 1. And that all those points represent P1. And then when you add them all up, you get 1. So this is just, I'm hoping that this is coming from probability and entropy. Yes, the chain rule. So the story exists for more theories. Okay, for now, so let's come back here. The purple dotted line, this is what a lot of us know. When we study probability for classical physics, what we do is when we study probabilities, we add them up, right? What's the probability that something's conditional probability? That's what I meant. When things add up, when we study probabilities, you usually add up the probabilities. What are the chances that things will happen? So that's given by this diagram here, inside the purple. And then when you go up bigger, when you start having like splitting, that's when people study the topic, probability theory, when things start to split. So there's interpretations, as we know. Now, when you go out to the bigger world, what do the red lines represent, the multiplicative lines? What do the black dots represent? What about these floating circles? What do they represent? We do not really know. We don't have any physics interpretation. You also have this blue line where things are being absorbed, right? Like these guys here can be absorbed and it pops out like a bubble, a dot. What kind of interpretations do we have? And also I mentioned about the chain rule in the previous slide, but we have not explored more further because people study information theory and geometric information theory. There's all entire topics that could be described in terms of diagrammatics, and that's completely new, but we don't have the time to study all that. But that would be,
What's the meaning of C1?
Oh, these are like scalar multiple, but we don't know physics interpretations, or in terms of particles or boson fermions, or we don't know. I mean, we have to sit down and think about it and try to see how things match up. They probably do, but we have not thought about it in other directions. We just know that locally this is given in probability theory, but everything else we are not exactly sure how to interpret all of this in terms of physics. And maybe there are more defects that we can introduce. Defects meaning the dots, codimension 1 defects, or maybe some more objects that in order to make the categories bigger, even enrich the categories.
The red one is the line defect, or is it not the defect?
Huh?
Okay, red one, red the open string. That's the line defect or
Yeah, when people normally talk about defects, there are submanifolds sitting on the cobordism. So here, the boundary points are zero-dimensional, and then you have this one-dimensional strings, which are the cobordisms. And then when you have dots sitting on the strings, those are called defects or submanifolds. Now, when you have circles, you can so you can study the same thing, but go higher dimension, go one-dimensional or two-dimensional. To replace the points, all these points, we could draw more points. Replace it with circles, and then when you do the cobordisms, now you have two-dimensional surfaces. So that's like 2 + 1. And then you can introduce defects, meaning you can introduce what Mikhail Khovanov talked about, like the seam lines, right? Or like the foams. That's when the foams start to come in. You can add one-dimensional defects and zero-dimensional defects. Codimension 1, codimension 2. And then the defects can sit on the string. The defects can sit on the one-dimensional strings or on the regions of the cobordisms, or even floating in space. So none of that has been explored. Yeah. So
you know, the red line, look at this kind of the bottom, top and bottom, and then you have C3, and then you have also red dot. Red dot is the point defect, and
yeah.
the line is the red line is the line defect.
Yes. Yes, but then like these are just multiplicative. Like we know mathematically, but we don't know if there's a deeper structure underneath.
Okay.
Right? Yeah. So mathematically, everything works out really well. Yeah. Also, John Baez, Tom Leinster, and T.D. Bradley, they consider like similar kind of diagrammatic interpretation for entropy. But their explanations would be completely different than what we did, what we are doing. It's very different. In our case, the monoidal category, it contains different kind of objects and morphisms. And then the red lines are actually, they correspond to multiplicative red lines that scale the block additive probability lines. And then in our story, Catalania's invariants all appear in our pictures, in our diagrammatics. We've also seen the entropies related to cohomology and cocycles. So one of the novel parts about our diagrammatic interpretation is that we have the appearance of a monoidal category of planar diagrams which controls the cocycles. So you have seen that you have this module U, or this U, which is the representation of group G, and you have this floating points, elements of U, and then they represent. You've seen floating points on the planes. You've seen lines on the network that are labeled by elements of G. And then you've also seen additive vertices, which contribute towards two cocycles. So this is the two cocycle in terms of multiplicative sense. The C is the two cocycle. Thank you for clarifying that earlier. And let me see. And then we've also seen like the wall which absorb and emit vertices. So we've also seen that in our diagrammatic story. So I would also say the entire story could also be studied. This is a story that works for Shannon's entropy, but there's also Rene entropy and generalized more entropies. So you could study how would you draw diagrammatics which fits into the entire framework as you generalize to more and more entropies. We have not worked on that either. There's many other entropies that we could study. We just looked at the easiest and simplest one, and then I'll continue to develop it, and turned out to be this paper. And that's all I have. Thank you so much for your time. Yes. Yeah.
Endomorphism of a given object.
Yeah.
How big it is?
The object?
Endomorphism
Endomorphism.
of a given object.
I'm not sure. I don't know.
So you have identity.
Oh, you have identity?
Is it very big enough?
I think if you just add only just the strings, it's not big enough. It's unique, right? It's, as we've seen, because the cobordism is unique. If you have two strings, You have merge and you also have merging and then splitting, but they also simplify. So it's identity again. Yeah.
Just few.
Yes. Not many.
Okay.
Uh-huh.
That's, I think, interesting. Okay. I think physically there's an anyway. Again, this is the
Oh, representations.
that's I think one of the things that's a good way to
Yeah.
understand it. How about this one there, this another there,
Uh-huh.
and then when you introduce the home method, and then can you analyze this one too? Okay. Working two.
Oh, two coordinates or two,
Just I think
the natural
sometimes
transformation.
You're calling the one of
Yeah, I think we could. I think we could, but we have not looked at it because you're going from object to objects and you have morphisms,
Yeah.
then you have the functors, and then you have the natural transformations. We have not gone too deep. Continue to build from this very simple diagrammatics. No. So it's very, I think we could, but we have not done it.
Also, okay, instead of the classical entropy and quantum
Yeah.
entropy, can you do you have this is what also a difficult question.
Uh-huh.
Can you calculate entropy on Von cells?
Entropy and which one?
Von Neumann algebra.
Kahneman.
For matrix.
Matrix. Yeah, I think. Okay, so we thought about it. We're thinking of similar kind of stories, but we're gonna have some kind of automorphism or like this rotational story. Yeah, so you have set of vertices to a set of vertices, but you have we allow rotations in order to allow the edges to actually represent these guys to actually represent matrices. Yes.
Yeah.
We have not developed much. We thought about it briefly, but that's all.
Can you apply 2D gravity? It's fine. But
Yeah.
The generally 3D, there's a 3D gravity try to understand on the different entropy by Von Neumann. In particular,
Oh yeah. Yes.
yes, I think that this is very nice.
Yes.
But still, you have classical.
Yes, that's classical. So like 5 minutes, right? So I would leave that as an open question, or maybe we could talk more on developing entire story for like the quantum setting, the quantum entropy. Yeah, that would be interesting. Mm-hmm.
So, whenever you order with at least the vertex,
Mm-hmm.
you're basically looking at the
Background.
the ribbon graph.
Okay. Oh yeah, ribbon graph.
So this is actually looking on ribbon graph Q66.
Uh-huh.
If you cut it out,
We're looking at only planar diagrams, but not higher genus or other surfaces. So that would also be interesting open question to study entropies on other surfaces. Right.
What you mean? What benefit? Yeah, we buy micro ribbon.
Yeah.
That's right.
basically just naturally live on a
That's right. Can apply on.
Another thing would be like if you know information theory or geometric information theory, can you come up with new invariants, very natural, canonical, simple invariants using diagrammatics? That would be another completely, because if you go through the books, you see that there's a lot of equations, and can they actually be restated in terms of something like this? Yeah. Oh, that's a good question. We did not work on that either. We have not. Probably it might work out. Young Buxton questions. Yeah.
Well, let's thank the speaker again.